Good morning, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. Today, I'm going to discuss on the derivation of Cramer Rao lower bound and its applications. So, let us start our discussion. So, first of all, let us start with the meaning of an unbiased estimator, that is, the point estimation is the use of statistic to estimate the value of some parameter of a population having a particular type of density. See, when you have a density function f of x comma theta, where theta is parameter, definitely you'll try to estimate the value of theta, where theta is the parameter of the population which is following this density function. Okay, then you'll try to estimate this value based on a sample as a single number, which is called point estimation. Suppose if you are estimating theta as an interval, then it is called interval estimation. If you are trying to estimate theta as a single number, theta naught, then it is called point estimation. Okay. Now, the statistic we use is called point estimator and its value is called point. That means the mathematical formula which we are applying on the sample data to estimate theta, the formula is called point estimator. And the final answer we got from the sample by using the formula is called point estimate. This is theta naught and this is the formula. Okay. Now, a desirable property for a point estimator phi of theta is that the expected value of phi is theta. That means, suppose you are trying to estimate the parameter theta of this population, where the population is being represented by a rectangle, and you are using a sample data to estimate theta, where sample is denoted by the circle. Now we are using a formula which is denoted by phi or phi, you can call phi. Now we call phi as an unbiased estimator. An unbiased estimator of theta if expectation of phi is equal to theta. That's what here he is telling, that the expected value of phi is theta. Then this phi becomes the unbiased estimator of theta, which is a required and a more important quality of an estimator while estimating the parameter. Okay. So because every mathematical formula is a mapping, and hence it could be treated as a random variable. Okay. So definitely you can write it as expectation of theta cap, because or phi cap. Okay, as because we are assuming continuous random variable, it could be phi cap into f of phi cap d phi cap should be equal to theta. That's what it is mentioned. That is the meaning of expectation of phi is equal to theta. Then phi is called the unbiased estimator of theta. There might be more than, so we have to tell an unbiased estimator. Okay. Now, often the process of making a point estimate, we must choose among several unbiased estimators for a given parameter. That means there might be not a single unbiased estimator for theta. Generally, there might be more than, say, alpha, beta, gamma, or 3 different unbiased estimator of theta. Then the challenge arises. We have to pick the better or good estimator of theta. So that means expectation of alpha is equal to theta, expectation of beta is equal to theta, expectation of gamma is equal to theta. So here arises the challenge, and here we must be able to pick the best one among these 3, that is alpha, beta and gamma. Okay. So, for example, suppose x1, x2, so on, xm are random sample from a normal population of mean mu and variance sigma square. You know that only odd events exist, even events automatically vanishes. That is what he's mentioning with this. Okay. And let the density of the function the f of x comma mu comma sigma square, that is you can understand this because it's normal distribution. You can understand it as 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma square. Okay. Now, it is well known that both the sample mean and sample median are unbiased estimator of mean. That means he is telling that for a normal distribution with mean mu and sigma square, both sample mean and sample median, okay, are unbiased estimators of population mean. Both are unbiased. So how to pick the best one or how to pick the more efficient one? When there are two choices, how to pick the more better choice which gives you more accurate estimation of theta? That is the challenge. So we need one more criteria. Okay. So that is called efficiency. That is called efficiency. That means when there are two or more than two unbiased estimators of parameter theta, say alpha comma beta, to pick the best one, we will take the help of efficiency. We will check which is more efficient when compared to the other, and basing on that, we will decide whether alpha is to be picked or beta is to be picked. What is efficiency? Let us look into the details. An estimator with a smaller variance is said to be relatively more efficient because it will tend to have values that are concentrated more closely about the correct value of the parameter. That means, see, when you have say alpha, beta, gamma are three estimators of three unbiased estimators of population parameter theta, that is E of alpha and E of beta is equal to theta, E of gamma is equal to theta. Then how to pick the better one among these three? Then this definition is telling that calculate the sigma alpha square, sigma beta square, sigma gamma square. Now check whose variance is smallest, whether sigma alpha square is lesser than sigma beta square, sigma gamma square, or sigma beta square is lesser than sigma gamma square, sigma alpha square. So you have to pick the variance which is least of the three, and the corresponding estimator will be the efficient estimator. That means variance decides the efficiency. Expectation decides unbiasedness, whereas variance decides efficiency. So that is what we call it. So according to this, an estimator with smaller variance is said to be relatively more efficient because it will tend to have values that are concentrated more closely about the correct value. I'll explain this meaning with help of diagram. Thus it follows to be more confident that our estimate will be close to the actual value as we would like. Furthermore, the quantity this is used to measure the efficiency relative to theta 2 is relative to theta 1. That is, if this is less than 1, we call theta 1 is efficient. If this is greater than 1, we call theta 2 is efficient. That's it, simple. So the ratio variance of theta 1 cap or phi 1 cap over phi 2 cap tells you which is efficient. If this ratio is less than 1, we call theta 1 cap, phi 1 cap is the efficient estimator. If this ratio is greater than 1, we automatically declare phi 2 cap is the efficient estimator of theta. The thing is, how to imagine this on a plane or geometrically. Let's see that. So for that, I'd like to take help of a slide. Now, see this diagram. Say this is the parameter theta which you would like to estimate. See, this is the distribution of the values of alpha. See, this is the distribution of values of beta, where both are the estimators of theta. Okay, based on the sample values of alpha and beta. When you plot the values of alpha beta based on different samples of size small n. Okay, let the values of alpha beta be like this. Then what you are observing here, if you observe more towards the right of here, you are observing more area, you are observing less area. That means the theta, the alpha is not balanced over its middle line. So this is called biased estimate. But here you are observing that about the middle line symmetry, that means equal area 50%, 50%. This is called unbiased. That means beta is unbiased estimator than alpha in estimating theta because the area has been equal. That means the data has been equally spread on either side of its central line. But whereas alpha, more area is been on right side and less area left side. That is not unbiased. Okay, so we consider beta here. That is first thing. So this is the way to geometrically analyze the unbiasedness of an estimator. Now, thing is, second one, efficiency. How to imagine efficiency? See this? Here, we are intending to estimate the theta. Suppose this is here also we are intending to estimate theta. Now, I am drawing a curve. Okay, this is alpha and this is the center line. You are observing that it is unbiased because the data has been spread equally on either side of the center line. Now here, also you are observing that this is beta is another estimator of theta. Here you are observing that data is equally distributed about the center line equally on either side. Now how to decide which is more efficient? Because both are unbiased here. Alpha is unbiased, beta is. So how to pick the better one? Then you look at the spread of radius of the spread. That means how long from the center the data has been spread on both sides. Say this number is some capital R. That means or meter or centimeters the data is set. And look at this spread of from the center on either side, say small r. Then when you look at both the diagrams, you will observe that r is less than, small r is less than capital R. That means this parameter is storing more data in less space from the center. That means within less distance you can cover all the data. But when come to alpha, you have to travel more distance to cover the data. So that means even though both are unbiased, beta is called efficient because its sigma beta, that is this spread is called sigma beta, okay, or sigma beta square is lesser than sigma alpha square. That is what you call efficiency. Now we are going to derive the proof of Cramer's law of Royal bond, which we have discussed in the last class. Okay, thing is what is the motivation behind Cramer's law of Royal bond? Okay, why we should learn it? See, practically we told that we learned that variance of alpha is less than variance of beta, and both alpha beta are unbiased. Then alpha is called efficient. But generally, practically, it's very difficult to find out whether alpha is efficient than beta or not through this definition. Practically, it is very difficult. So what we have to do? We have to seek an alternative. So one of such alternatives, the best proven alternative is Cramer's law of Royal bond. So if you want to check whether alpha is efficient than other unbiased estimators, you have to calculate variance alpha. For that, it gives you an approximation through this formula. This is called Cramer's law's lower bound. And in the similar way, you can calculate variance of beta's lower bound by using the same formula. Then you can easily estimate whether alpha is better or beta is better or efficient. So that is what this best alternative in order to check whether which is the efficient estimator. Okay, let us look into the meaning and proof. See, um, suppose he is telling that we are trying to estimate theta with help of a formula phi cap on a sample x1 or random variables x1, x2, so on, xn. Okay, then you can find the lower bound of variance of theta cap. Variance of theta cap. If it satisfies this condition, what is the condition? The partial derivative of n times integral of the function phi of x1, x2, so on, xn, n tuple multiplied with the individual and independent density function. That means x1 will have a density function f of x1 comma theta, and x2 will have a density function f of x2 comma theta, and x3 will have a density function f of x3 comma theta. Okay, then it is telling that the partial derivative of n times integral of phi of x1, x2, so on, xn with f of x1 comma theta into f of x2 comma theta into f of x3, like that, is equals to n times integral of phi of x1, so on, xn dou by dou theta of product of the density functions. So if this condition satisfies, then you could tell that the variance of phi cap will be at least or greater than or equal to reciprocal of this number. That's what's the Cramer Rao lower bound. This is called Cramer Rao lower bound for variance of theta cap. Okay, this is proposed by Cramer and our great Indian statistical and mathematician C.S. Rao. That is why it is named after them. Okay, now here we call this as with a special name called Fisher's information, or this is denoted by I of theta, which is called Fisher's information. So by looking at this, you'll understand that variance of theta cap will be inversely proportional to the Fisher's information, directly proportional to the reciprocal of Fisher's information. That's what you could tell. Okay, now log likelihood is nothing but the logarithm, natural logarithm of the maximum likelihood function. That is what we have written here. Of course, we have seen it, and this is Fisher's information. Now, and efficiency of a parameter theta phi cap is defined as 1 by I of theta into 1 by variance of theta cap. From that lower bound you can estimate, and always from this Cramer's Rao inequality, okay, you will understand that this is variance of theta cap into I of theta is greater than or equal to 1. That is why 1 by I theta into 1 by variance of theta cap will be less than or equal to 1. That is why this is efficiency. We denote it as E will be always less than or equal to 1. Okay, that's what written here. Now let us look into the proof of the theorem. That means the derivation of Cramer's Rao lower bound. We prove this theorem like this. We assume that the phi of x is a function phi cap of n tuples. We assume that our estimation phi cap of x depends only on the sample values, not on theta. So what we have to assume, phi of theta of x1, x2, xn completely depends on the values, but not on theta. It is independent of theta. Okay, and we know that this is because we calculate the efficiency for only unbiased estimation. That means automatically we have to understand that the phi cap is an unbiased estimator of theta, which is the population parameter. Okay. Now, when you assume that and bringing theta to the left side, that is expectation of phi cap minus theta is equal to 0. Expectation of phi cap minus theta is equal to 0, because expectation of constant is constant. We know that expectation of is constant. Theta could be written as expectation of theta. Okay, that is why this becomes expectation of phi cap minus theta is equal to 0. Okay, now what is the density function? You know that, let me once make you to recollect the definition of expectation of a continuous random variable. Okay, see, expectation of a continuous random variable x, whose density function of is f of x is nothing but integral f of x into f of x dx, where the limits rise between minus. Here the density function is phi cap minus theta. That is means phi cap minus theta is the variable. Sorry, this is x, e of x, and the density function is nothing but the product of individual density functions, because they are all independent. Independent means joint density function will be the product of marginal density functions. That is why this will be with the help of this here x in the place of x. This we have to write. That's what we have written, and in the place of f of x we have to write the product of n density functions of each random variable x1, x2, so on, xn. That is why we got this. And dx means again it will be product of dx1, so on, dxn. Okay, now, and this is equal to 0 from this we observe. Okay, now let us recap what we have with us. We have two conditions in order to reach the in order to prove the Cramer Rao lower bound. We have two conditions, that partial derivative of n times integral will be n times integral of partial derivative of n times the product of density function. This is the one condition. Second condition, variance of phi cap will be always greater than or equal to reciprocal of Fisher's information. These two conditions we have from the data. That's we have mentioned here. Now, we are, for the sake of simplification, we are denoting entire this thing as f of or some as phi of x comma theta. We are denoting this as phi of x comma theta. Okay, or x bar, where x1, x2. Okay, and we are denoting this as d of x bar. Okay, then what happens? And we denote, for the simplification sake, we denote it as phi cap minus theta. Okay, so automatically this will be briefed into this version. This will be compacted into this version, differentiating both sides of this equation. Okay, with respect to theta, differentiating both sides of this equation with respect to theta, and using the assumption of equation 2.1, this will be 0 dou by dou theta of, okay, dou by dou theta of these things. Understand? So dou by dou theta of this. See, from this we'll apply UV rule. You know, derivative of u, d by dx of uv will be u into derivative of v plus v into derivative of u. So by applying uv rule for this, we will get derivative of u into v plus u into derivative of v. That's what we got. So 0 is equal to n times integral of u derivative of u into v plus n times integral of v into u's derivative. That's what we obtained. Okay, now here we know that phi cap is independent of theta. So what it is a constant. You can treat it as a constant with respect to theta, because it doesn't contain theta. Okay, it can be treated as a constant while differentiating with theta. So derivative of a constant is 0, and derivative of theta with respect to theta is 1. So automatically it becomes minus 1. Okay, so what happens? This becomes minus 1. Then we get this step. Because it's become minus 1, we will get that step. Okay, now This is remaining as the same. And here, what is this? This is nothing but minus integral of f of product. This is a product of density function, that is f of x1 comma theta dx1 into integral of f of x2 comma theta into d theta, so on f of xn comma theta into d theta integral. Okay, where minus infinity infinity, because that is trivial. Even though we are not writing limits, we have to understand that it is minus infinity. Okay, you know that sum of all probabilities is always, so total probability is always one. Total probability is all, that is the major condition of density function. So sum of minus infinity f of x dx is equal to 1. That is why this becomes 1, this becomes 1, so on, this becomes 1. So how many times we have to multiply? These are n ones, because x1, x2, so on, xn. So all 1 into 1 into 1 for n time, that means 1. So entire thing becomes 1. So this entire thing becomes 1 because it is minus 1. So what we have obtained? We obtained that this entire thing becomes minus 1 and this remains as it is. Okay, this is what we understood from the derivation. Now our thing is to evaluate this integral, this n tuple integral. In order to evaluate, first we have to expand what is the partial derivative of this product of n density function phi, because phi of x bar comma theta means it's a product of n density function. So first we will do that in a separate way. So let us take dou phi of x bar comma theta, which is where phi of x bar comma theta is nothing but f of x1 comma theta into f of x2 comma theta into f of x3 comma theta, so on, f of xn comma theta. So by taking that, we reach that dou theta of f of x1 comma theta, f of x2 comma theta, so on, f of x comma theta. Now, what is this? This is a partial derivative. That means we can apply UV rule. Derivative of first into remaining plus partial derivative of second into remaining, like derivative of UV rule, UVW rule, U into derivative of V plus VW into U's derivative plus UW into or UV into W's derivative. Like that we can write in the same way by applying UV rule for n times, we will get this expansion. Okay. Now what we are going to do? We are going to use a simple mathematical formula from chain rule. According to chain rule, suppose g of x is a function. Okay. Then log g of x. We want to calculate the derivative of log g of x. This will be, if you treat this as x according to chain rule, this will be 1 log x derivative 1 by x into x derivative, that is g dash x. That means g dash x by g of x. From this, what we get? G dash x is equal to g of x into d by dx into a log of g of x. Okay, this is what we understand. Or what you get? Yes, you can even not write this. Just here you can stop. So derivative of log is nothing but g dash x by g of x. That you know very well. By using this, we are going to write dou g by dou theta is equal to g into dou log g by dou theta. That means we are taking this to here. Division becomes multiplication. We are getting this. Now we are applying this here in the place of dou f of x1 comma by f theta. That is here in the place of g. We are assuming f of x1 comma theta. This becomes f of x1 comma theta into dou by dou theta of log of f of x1 comma theta. In the same place, in the same way, here if you assume f of x, dou by dou theta of f of x2 comma theta, it could be written as f of x2 comma theta into dou by dou theta of log of f of x2 comma theta. So in the same way we proceed, we are getting this uh, this equation, that is uh, we are getting this summand, that is summation of I is equal to 1 to n dou by dou theta of log of f of xi comma theta, okay, into f of, that means if we put them in a compactified form, we will get this. Okay, now because this is simply, we can denote this as phi of x bar comma theta or x arrow comma theta. Okay, product of density functions and we have already given this notation, and this is completely independent of because it's a constant and independent of theta. The constant can be written out. This can be treated as k. This is nothing but this, and we can keep it outside. We'll get this. Okay. So what we have arrived at, we have arrived at that dou phi of dou theta is nothing but phi of x comma theta summation dou by dou theta of log of f of x I comma theta. This is what we arrived at. Now, by substituting this, so we got this value, right? Now what we have to do, we have to substitute this value in this equation, because we have already obtained this equation where we found this as this summation. So we let us substitute this in the place of this. We are getting this integral. Why 1 here? Let us check. See, minus 1 goes to this side, becomes plus 1. That is what we have written over here. So we got this particular thing. Okay. Now what we are doing, we are just doing a simple mathematical manipulation, that here we are seeing phi of x x cap theta or x arrow theta, which is a product of n density functions, right? Now we are trying to write this as phi of x cap theta as v of x cap theta square root into square root of v of x cap theta, because product of square root means root square will be cancelled. That is why we are writing that, and we are accompanying one of these square roots with summation, and we are writing other outside the summation. That is why we have obtained this. Now we got this equation. So now let us square. That means let us squaring on both sides. Squaring on both sides means 1 square, and squaring on both sides means we can understand it as whole square, right? Whole square. Then what happens? Then we will get, because we will get by using Cauchy's square inequality, which says that integral of f of x into g of x is less than or equal to integral of f of x into integral of g of x. Okay, by using Cauchy's square inequality, we could split this as less than or equal to integral of this can be treated as f of x, g of x, sorry, whole square about the inequality. Yes, so this could be split as integral of this into n times integral of this into n times by using Cauchy's square inequality. Okay, here we are assuming f g of x is also f of x, then you will get this f of x whole square instead of g of x. Then you can understand this. Okay, so we got this by using Cauchy's square inequality. Now please carefully observe this. What is this? It is nothing but, it is like integral x bar xi minus mu whole square or x minus mu whole square dx. What do you say about this? when you see x minus mu whole square dx, okay, you immediately come to understand this is variance definition, because we have seen this in our probability and statistics. This is nothing but variance definition. Now here in the place of x minus mu, we are observing phi cap of x as x and mu as theta. So what it happens? It happens variance of phi cap of x. That's what we are observing. This okay. This becomes, so what happens? We will get that 1 less than or equal to variance of phi cap into n times integral of summation I is equal to 1 to n dou by dou theta of log of f of xi comma theta whole square phi of xi x cap theta. Okay. Now, so thing is, we have to find what is this integral. If we find this, and we prove that this particular thing will be equal to expect n times of expectation of this, we have successfully obtained the Cramer Rao inequality. So all the thing we have to do is we have to prove this n times integral of summation of dou by dou theta log of f of xi comma theta whole square phi of x bar cap comma theta is equal to n times expectation of this dou by dou theta log f of x comma theta whole square. For this, we are considering this n times integral. Now, here we are splitting the summation as summation I is equal to 1, j is, because this whole square means we can understand it as summation I is equal to 1 dou by dou theta of log of f of xi comma theta into summation I is equal to 1 to n dou by dou theta of log of f of xi comma theta, because a square can be written as a into a. That's what we have done. But in the place of I, we are just writing as a formal notation j. Okay, then we will get this step. So we just have written the square. A square means a into a. So this is a into a. That is what we have written here. Now, here summation, we are just bringing the summation outside of integral, and integral inside, summation outside, we are getting this step. That means summation written outside and integral written inside, we got this step. Okay. Now, we are writing this as I1 plus I2, where I1 and I2, what is I1 and I2? Let me explain in the next slide. See, I1 is nothing but n times integral of summation of I is equal to 1 to n dou by dou theta of log of f of xi comma theta whole square, and I2 is nothing but summation of I comma j n times integral of dou by dou theta of log of f of xi comma theta into f of x. That means here what we are observing that there is possibility of at one place the I value is equal to j, and remaining places I naught equals to j. So basing on that, we are splitting the summation and integral into two summation. We are splitting entire thing into two summations, that is I1 and I2, where I1 takes care of if I is equal to j values, and I2 takes care of I not equal to j values. That's what we have written. Now, we are going to prove that this I1 will be n times of expectation of this, and I2 value will be 0. This is what we are going to show. If we prove this successfully, we will be complete the proof of Cramer Rao law. Okay. Now I1. I1 means the n times integral of summation I is equal to 1 to n dou by dou theta of log of f of xi comma theta whole square phi of x cap comma theta dx cap. Now, the summation comes out, and see here again, yeah, what is phi? Let us just recap. What is phi? phi cap comma theta is nothing but product of f of x1 comma theta into f of x2 comma theta, so on f of xn comma theta, right? Now here, if you take the summation, somewhere you will get f of xi comma theta, right? So what he's doing, he's just taking that f of xi comma theta into separate and remaining all into product. That means he's just bringing this f of xi comma theta into separate and merging remaining as a single product, and that is why we got this step. Okay, that means has taken only that I and remaining all density functions are put together. Now again, if you see that, see f of x1 comma theta dx1 minus infinity infinity into this is nothing but f of x2 comma theta dx2 minus infinity infinity, so on f of xn comma theta dx1 integral minus infinity infinity, except for this one, that is f of xi comma theta. We considered everything. Okay. Again, we know that the sum of all probabilities is 1 under density function. So this will be 1, this will be 1. So hence all the products will be 1. That is what we have written, 1 power, because there are n minus 1 integrals and each integral is 1. So all becomes 1 power n minus 1. That is why this becomes 1. This becomes 1. So we will be reminded with this thing only. We will be reminded with this thing only. Now, my question is, if you see this, just look at this thing only. Just look at this thing only. It looks like if you treat dou by dou theta of log of f of xi comma theta as yi, and if you name f of xi comma theta as f of yi, okay, then it would be like integral yi f of yi minus infinity to infinity and dy, right? That means which is like integral minus infinity to infinity x into f of x dx, which is nothing but e of x. So that is why we could understand this is nothing but, if you treat this as y, this will be expectation of y, that is e of y. Okay, and you know that this expectation is always a number. Expectation of any variable is a number. You can understand it as k. So what happens when you understand this expectation as a number k comes out, it becomes summation I is equal to 1 to n of 1. So how many times you are adding 1 for n times? So what it becomes? K into 1 plus so on 1 n times. So it becomes nk. So you are getting n into k, that means n into expectation of dou by dou theta of log of f of xi comma theta whole square. Now we have obtained successful in the first mission, that is I1 is equal to n times expectation of dou by dou theta of log of f of xi comma theta whole square. The second mission is we have to show that I2 will be 0. How to show that I2 is 0? What is I2? I2 is nothing but n times integral of dou by dou theta of log of f of xi comma g and theta and dou by dou theta of f of xj comma theta, where I naught equals to j. Okay, now you can separate, as I told you here. This is phi is nothing but phi of x cap comma theta is nothing but f of x1 comma theta, f of x2 comma theta, f of xn comma theta. You could separate it as with the help of I and with the help of j and remaining all. Okay, that means we are making ith component aside and jth component aside, remaining all we are clubbing and putting into an integral, separate integral. Then this would be automatically 1, because the sum of all probabilities under density function is always 1. This will be 1 power n minus 2, because they are n minus 2 integrals. So it automatically becomes 1. So we have to deal with this thing and this thing, right? Now, so we got, now just look at this. How do you, it looks like, it's look like y into f of y dy, and it's look like z into f of z dz. So you know that this is expectation of y, and you know that this is expectation of z. We understand that this is expectation of dou by dou theta of log of f of xi comma theta. This is expectation of dou by dou theta of log of f of xj comma theta. Now, what we have to prove, our intention, this is I2, our intention is I2 is equals to 0. So what we have to do, we have to prove that this is 0 and this is 0, then we are done, right? So now we are going to do that. Now for that, let us just recap this thing. If f of x comma theta is a density function, then 1 is equal to integral of minus infinity to infinity f of x comma theta dx. That we know, sum of all probabilities on density function is always 1. Okay. Now just differentiate this with respect to theta. Differentiate with respect to theta partially on both sides. Okay, we are going to partially differentiate with respect to theta on both sides. What is one's derivative? One's derivative will be 0, and this will be dou by dou theta. Okay, because integral and derivative can be switched mutually. We can take it in and we can take it out. We are getting this. So what we observe, integral of dou by dou theta of f of x comma theta is always 0. Okay, now by using this as a formula, now we are going to do one small thing here, that is we are going to use this formula that dou g by dou theta is equal to g into dou by dou theta of log of dou g by dou theta is equal to g into dou by dou theta of log of g of theta. This is the formula just we discussed in the previous slides. Now we are going to use that. So that would be dou by f of x comma theta into dou by dou theta of log f, or we can understand it as multiply and divide with f of x comma theta. This is nothing but f dash by f. This is nothing but derivative of log of f. Okay, because you know that derivative of log of f is nothing but f dash x by f of x. By using that, we reach this step. This is nothing but expectation of this. So expectation of dou by dou theta of log of f of x comma theta is always 0. That is what we obtain. By using this, this will be 0 and this will be 0 and the product will be 0. That means I2 will be 0. So what we have proved that I2 is 0 and I1 is this number. By using that, we came to know that this is n into information of theta, that is Fisher's information, then this is 0. Okay. And about LHS, what do you say? LHS is so we 1 less than or equal to variance of phi cap into n into I of theta. That is what we arrived at. Okay. So when you take multiplication becomes division, that means variance of phi cap, variance of phi cap is nothing but 1 by n into Fisher's information. Okay, greater than or equal. So this is the Cramer's law of inequality. So we are successful in establishing the Cramer's law of inequality in this proof. So of course it is lengthy and intrinsic, but it is very important to understand the applications of Cramer's law. Okay, now yes, if we have a quick glance over the proof, we started with this. Okay, we started with this because it's an unbiased. We have this, and by writing the definition of expectation, we got this, Okay, by writing the expectation we got this. Then by having a notation of product as this, and the product of derivative as this, we will get this. And then partially differentiating with respect to theta on both sides, we have arrived at this. And by using UV rule, u into v's derivative and v into v, we have arrived at this. Then because this is independent of theta, constant derivative is 0 and theta's derivative is 1, we got this minus 1, and we left with integrand minus phi of x cap comma theta, which is product of n density functions. So the integral will be product of indefinite integrals of f of x1 into theta, f of x2, so on. All sum of our all probability sum to density function is 1, we will get this as 1, so this becomes minus 1, and we are left with this. And minus 1 goes to this side, we get 1. Okay, and by using again, by using when we comes to this, okay, and when we use the this definition, okay, this we are trying to find this again using UVW rule, we get this, and we know that f dash x by f of x is derivative of log f of x. By using that, we have this formula, and we got finally this summation, and by substituting that in the obtained integral, okay, and squaring on both sides, we get this, and by using Cauchy's square inequality, we have obtained this. Okay, now this is nothing but variance, because I told you if you treat this as y, this will be f of y, so it would be like expectation of, or no, sorry, this is y minus y bar expectation y minus y bar whole square integral f of y. That is why this becomes expectation of y minus y bar whole square, which is nothing but variance of y. That is why this becomes variance of phi cap, and we are left with this. Now we have to find this. Okay, now we have taken this, and we are planning to prove that this is nothing but n times of this expectant, which is nothing but information, Fisher's information. So for that we started with this, and we split this as a into a square is equal to a into a. That's what we have written, and then we have split this into two summations by using I is equal to j and I not equal to j. Okay, then we have got I1 and I2, and our intention is to prove that I1 will be n times of Fisher's information, which is n into expectation of dou by dou theta of log of f of xi comma theta whole square, and our intention is I2 is equal to 0. So to prove that I1 is this and I2 is this, we started with I1, and again we used the meaning of phi, and we kept only ith term and remaining all clubbed. You know that every density function minus infinity is 1, so this will becomes 1 power n minus 1, and we will be reminded with this. This is nothing but it's look like e into y into f of y, that is means expectation of y. That is why we got this, and this is a constant can be written out, so this is summation 1 I is equal to 1 to n into k, so this becomes n, so nk, that is n into Fisher's information. Now our I2, we have to prove I2 is 0. Okay, for that we got I2 as this, because as I told you, this is ith, this is jth, remaining all clubbed, this becomes 1 power n minus 2. By using sum of all probabilities equals to 1, this becomes okay. Now we have to prove that this expectation is 0, this expectation is 0. For that we have considered the general formula of sum of all probabilities is equal to 1. We have partially differentiated with respect to this, one derivative is 0, partially derivative of f of x comma theta with respect to theta, and by using f dash x by f of x is equal to derivative of log f of x. We can multiply and dividing with f of x. We can club this as derivative of log f of x. So we got this. This is nothing but expectation of this. So expectation of dou by dou theta of log of f of x is 0. By using that, this is 0, this is 0, and hence I2 is 0. When I2 is 0 and I1 is n times of, then what happens? Yes, this becomes n times of I of theta, and this becomes 0. Okay. When that happens, here we have proved that this is we have proved we arrived at this by Cauchy square generality, and we have obtained this as n times of Fisher's information, and hence we are successful in proving the Cramer's law of lower inequality. Okay, now we will see some applications of Cramer's law lower bound, and with that we will conclude the lecture. So, in estimation theory and statistics, the CRLB expresses a lower bound on the variance of unbiased estimators of deterministic parameter. That means it helps us in finding the lower bounds of a parameter of the population distribution, which is unbiased. That is the most important application. The variance of any such estimate is at least as high as the inverse of the Fisher, and also it helps us to find out Fisher's information in information theory. Equivalently, it expresses an upper bound of the precision of unbiased estimate. That means because variance of theta cap or theta cap is nothing but greater than or equal to reciprocal of n times of Fisher's information. Okay, this is called precision. So it will be direct proportional to the precision. That is what it is. So there are three applications. One is it gives us the lower bound of unbiased estimator, and it gives us a calculation on Fisher's information and a calculation on precision. So three applications are well known about CRLB. With this, I would like to conclude the lecture, and we'll meet with another interesting topic in another lecture. Thank you all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.